Hello children, welcome back once again. Now we discuss quick revision of chapter Oscillations. In this chapter we mainly focus on simple harmonic oscillations. What do you mean by simple harmonic oscillation? Simple harmonic oscillations are simplest of all harmonic motions. For any motion to be repeated periodically, there should be one of the important properties of the oscillating system. That is, there should be a restoring force. That restoring force should be always directed towards a central position or mean position. There should be a mean position through which that object should move here and there, to and fro, up and down. That type of motions are called oscillations. The time period of that oscillation is the smallest time interval after which that motion is getting repeated. Periodic time, reciprocal of which is called frequency. There should be a restoring force, and that restoring force should be expressed as a function of position. And that force should be of this form, which is F is equal to minus k x. The power of x should be 1. Then only this motion is said to be simple harmonic. So this is the necessary and sufficient condition of a motion to be simple harmonic, that F is equal to minus kx. If it happens to be the square of position x square, x raised to 4, x raised to 6, any even numbers appeared as the power of x, that will not be oscillatory. Instead, that motion would be in a straight line. But if the power of x is 1, 3, 5, 7, then that force is having restoring property, due to which that motion can be simple harmonic. Motion can be harmonic, and is simple harmonic only when the power of x is 1. So F is equal to minus kx is the condition for simple harmonic motion. Condition for simple harmonic motion. So this can be also be expressed as F can be written as mass into acceleration. Acceleration is expressed as second derivative of position with time. So m d square x by dt square is equal to minus kx. That is m d square x by dt square plus kx equal to 0. So d square x divided by dt square plus k by mx is equal to 0. This is the quadratic equation in x. Its solution can be found mathematically, and you may get x is equal to a cos omega t, or x is equal to a sin omega t, whatever. For which x can be represented as the position which varies with respect to time simple harmonically. So force should be of this form, position should be of this form, then the respective velocity, acceleration, all that we can find out. So this is the quadratic equation. Here this coefficient of x has some meaning. That will be written as d square x divided by dt square plus omega square x is equal to 0, where that omega square is the coefficient of x. So omega square is equal to k by m, and omega is equal to root k by m. Then time period is periodic time, 2 pi by omega, that can be written as 2 pi root m by k. These all are the features of simple harmonic motion. Okay, then you can express x is equal to a cos omega t plus phi, where a stands for the amplitude of position, amplitude of x. X stands for position at time t. A stands for amplitude, means maximum displacement, maximum position from mean position. Phi stands for the initial phase angle. Okay, that will tell you what phase angle is there initially at t equal to 0 from the reference point. For example, at t equal to 0, you put t equal to 0, omega t becomes 0. Then you get x is equal to a cos phi. Okay, but if phi was equal to 0, at t also equal to 0, listen, t equal to 0, phi equal to 0, then x would have been a. So x is equal to 0 at x is equal to a at t equal to 0 and phi equal to 0, x is equal to a. That is the amplitude. So at t equal to 0, if initial phase is 0, the initial position is maximum. Like that, as time changes, position changes periodically and also symbol harmonically. That is x is equal to a cos omega t plus or minus pi. That may be plus or minus pi. That may be either sine or cos. Okay, sometimes you may use y equal to a sine omega t plus or minus phi, like that. If there is no initial phase, things are very easy. Okay, also this type of equations can be easily generated by using uniform circular motion executed by a particle over the perimeter of the circle whose radius is a. At t equal to 0, the particle was at this point. At tth second, it has described an angle theta which is equal to omega t. Theta can be written as product of angular speed and time interval. That means the particle has taken t seconds to cover this much of distance in the anti-clockwise direction. The radius of that circle is, radius of the circle whose center is at O is A. Then dropping a perpendicular from the tip of that radius vector onto x-axis, you may get foot of that perpendicular at the point M. So the distance from O to M may be measured as x. That may be written as x is equal to a cos omega t. We have further dropped that perpendicular from that particle onto y-axis whose foot is n. So that distance may be written as y. So y can be measured as a sine omega t. That is the coordinates of the particle at t seconds is x comma y. So x coordinate can be found as a cos omega t, y coordinate a sine omega t. Then squaring and adding both of these equations, you get x square plus y square equal to a square, which is nothing but the equation of circle, which is the trajectory of this particle. So that particle is undergoing a circular motion. More than that, the circular motion is at constant speed. Speed of the particle is a constant. But you see, the projection of that particle dropped onto each of these diameters. What happens to this x projection, that is x coordinate? X coordinate is also changing continuously with the time. X coordinate varies periodically as a cosine function. X equal to a cos omega t is a simple harmonic motion. So x as well as y each executes simple harmonic motion. But the particle executes circular motion. Particle executes circular periodic motion. The foot m and n, m comma n, m as well as n, both the foots over the mutually perpendicular diameters execute simple harmonic motion as well as periodic motion. Okay, both are periodic. But circular motion is periodic but not simple harmonic because it is not oscillatory. A motion is simple harmonic only if it is periodic, also oscillatory. The angular displacement should be very small, extremely small. Then only the motion is regarded as simple harmonic. So x equal to a cos omega t is our reference. X is equal to a cos omega t. Let us begin as the cosine function as the reference. Now taking the first derivative, v is equal to minus a omega sine omega t. That is, we can also be written as minus omega root of a square minus x square. Next derivative, a equal to dv dt, that is equal to minus omega square a cos omega t. That can be written as minus omega square into a cos omega t is x. So this minus sign says that acceleration is directed towards the mean position. Acceleration is already directly proportional to the displacement. So phase angle between acceleration and displacement is 180 degree. Phase angle between acceleration and displacement is 180 degree means if acceleration is at an instant directed towards negative x-axis, position is directed towards, displacement is directed towards positive x-axis. If acceleration is in the positive x-axis, displacement is in the negative x-axis. The phase angle between acceleration and displacement is 180 degree. Okay, from these all equations, let us conclude. What is the maximum velocity during oscillation? The maximum of position x maximum is equal to a. Similarly, what is V maximum? V maximum can be written as a omega when cos omega t equal to 1. Its modulus. Similarly, modulus of the maximum acceleration can be omega square into a. So maximum velocity a omega, maximum acceleration a omega square. Okay, based on that many questions are frequently asked. Last mains paper, this question was seen when maximum velocity equal to maximum acceleration numerically. What is the condition? Modulus of V max is equal to modulus of A max. Modulus of V max is equal to modulus of A max. That is, A omega is equal to omega square A. Omega gets cancelled. A gets cancelled. So we get 1 omega remaining, omega equal to 1. What do you mean by that? Omega is 1 radian per second. That is, time period is 2 pi by omega is 1. So 2 pi by 1, that is 2 pi seconds, that is 6.28 seconds. So the periodic time is 6.28 seconds. Okay, that's simple harmonic motion. This is one of the popular exercises that have been asked so far. Now, position, velocity, acceleration. Velocity has two equations by heart. Acceleration also has two equations. Now, there are many other popular questions based on this. You have to exercise all this, whatever we discuss here. During when the particle is executing simple harmonic motion over this arc. Simple harmonic motion may be over an arc or over it may be a straight line, linear harmonic oscillation. It may be angular simple harmonic motion like this, whatever. It would have an amplitude. It would have an amplitude on either side. Suppose it reaches half the amplitude. Suppose it reaches 70% of its amplitude. The times taken. Suppose here time is 0. You start time 0 here. Half the amplitude. This is a by 2. This is a. And this is a by root 2. By heart all these times. Time taken by the particle to reach 0 to a by 2. We are moving from mean to extreme. So use this formula y equal to a sin omega t, because at t equal to 0, sin 0 is 0, so y is equal to 0. That's why displacement is 0. So reference is sin reference. Okay, now y can be a by 2. So sin omega t is 1 by 2. So you get t as continuing t by 12. So this time interval you get as t by 12. You continue this, then you get t by 12. Now time interval from a by 2 to a would be t by 6. Okay, for same change, same time, while it coming back here to here, time t by 12. Coming back here to here also time t by 6. Now, what is the time taken from here to here, a by root 2? That is t by 8 seconds. Then what about this time? That also would be t by 8. What is this total time? That is T by 4. That is 1/4 oscillation. So mean to extreme time taken is T by 4. Extreme to mean again T by 4. That is T by 4 plus T by 4. T by 2 half oscillation is over. Now T by 2 rest of the half oscillation. Now full oscillation is over. So mean to half the amplitude T by 12. Mean to 1 by root 2 times amplitude. 1 by root 2 is approximately 0.7. So mean to 70% of amplitude is time T by 8. From 70% of amplitude, the rest of the 30% of the amplitude also covered in same time. So distance traveled may be different because close to the mean position, the oscillating body is faster enough for same change, same time interval. Okay. In one of the previous papers, I have seen a question that what is the time taken by this body oscillating from mean to extreme to cover between y equal to a by 2 and y equal to a by root 2. Up to a by 2 T by 8. Up to a by root 2, up to a by root 2 T by 8. Up to a by 2 T by 12. So what is that time interval? T by 8 minus T by 12. Okay, that time interval, like that time intervals may be asked. You try to by heart all this. Standard results. Okay, so we have learned position, velocity and acceleration of simple harmonic motion. Okay, now one of the applications of simple harmonic motion is a spring mass system. Spring mass system. Let us take the example of a spring mass system. In the spring mass system, you consider a spring. We have to practice massless spring or light spring. A massless spring when suspended, no mass. Spring has no mass. Also, there is no mass attached. So it doesn't have any extension. Unloaded spring has no extension. Now you load by using a mass at its end. Let that mass be M. Now this is the extension produced by the load. Let that extension be E. The force exerted by the mass is mg. Force constant is K. So the restoring force as the spring has displaced through an extension E is Ke. For equilibrium, mg is equal to Ke. Students, you by heart, m by k equal to E by g. M by k equals E by g, or mg is equal to Ke. Now do one thing, you pull this spring slightly below and leave. The new extension may be X. Then the forces are mg plus pulling force. Pulling force is also there. For restoring force will be Kx plus Ke, or K into E plus X. Now you leave Fp, pulling force you leave, what happens? With the presence of pulling force, there is an equilibrium of all these four forces. But in this absence of this pulling force, there is no equilibrium. There is a net force acting in the upward direction. That is Kx plus Ke is the upward force, which is greater than mg by an amount Fp. That is minus mg is the unbalanced force. Ke plus Ke minus mg happens to be the unbalanced force, that is equal to ma. There Ke is exactly equal to mg. So Ke and mg, as they are equal, also the signs you can see, one is plus, the other is minus, so that cancels. So very simple equation, Kx equal to ma. But we know acceleration is directed towards mean position. So to show that, you place a minus sign. Then a is equal to minus k by mx, a proportional to minus x. This is the condition for simple harmonic motion, or f proportional to minus x. Restoring force, hence acceleration directly proportional to negative of displacement. Okay, where omega angular frequency root k by m, time period of the spring mass system is 2 pi root m by k. So this part is very, very important. Don't forget to study this by heart. Spring mass system, acceleration, time period, frequency. Also this relation mg equal to ke. Here E is the notation used for showing the extension produced by the load alone. Okay. Now, if you try to oscillate the spring in horizontal configuration, then maybe on a frictionless surface, then also the time period is unaffected by gravitational forces. That's why time period seems to be same. So for vertical as well as horizontal oscillations of a spring, time period remains constant. Time period only depends on mass at the end of the massless spring as well as force constant of the spring. Nothing else. That's why you can oscillate the spring mass system in a falling lift, freely falling lift with the same period. You can oscillate at the center of earth with the same period. You can oscillate the same in an accelerated cart. You can oscillate it in a liquid, provided it should oscillate. The mass of the block should be sufficiently larger so that it can oscillate underwater. Okay. So wherever in satellite, in outer space, wherever you can oscillate the pendulum, spring mass system with same periodic time. Now, if you cut a spring into equal pieces, spring constant k on cutting each of those pieces, spring constant would be 2k. Formula for force constant we have learned, k as YA by L. Formula force constant k as YA by L. Area does not change on cutting the spring like this on transverse bisector. Y does not change. Young's modulus only depends on material. Length is halved, then k has doubled. So when you cut a spring into 3 equal pieces, what is the spring constant of each part? 3k, 3k and 3k. Okay, if you cut into different ratio, suppose the length bears the ratio 1:2, spring constant bears the ratio 2:1. So length of first spring may be L by 3, length of second spring may be 2L by 3. Okay, like that L1 by L2 is 1:2. Then what will be K1? K1 will be the spring constant of this shorter one, that is greater, 3k divided by 1. K2 equal to, what is the sum? 3k. 1 plus 2, 3 divided by 2. So 3k and 3k by 2. You see, you can develop a shortcut based on this. See, L by 3. L by 3. From where did you get this 3? 3 is 1 plus 2. So 1 plus 2, 3. 3 by 1. 1 plus 2 by 1. 1 plus 2 by 2. 1 plus 2 by 2 is this. So longer one will have smaller spring constant. Shorter one will have larger spring constant. This is the way by which you divide. Then you can find out the periodic time ratio. T proportional to T equal to 2 pi root m by k. So T proportional 1 by root k. From the uncut spring, you have the uncut spring when oscillated with a mass period is T. You cut the spring into two unequal masses, unequal lengths whose length in the ratio 1:2. What is the periodic time when the same mass is oscillated with the shorter spring? Shorter spring has spring constant 3k. That's why k would become 3 times. So period becomes 1 by root 3 times. Period would decrease. As k increases, period decreases and period becomes 1 by root 3 times. Okay, like that questions may be asked. Now springs you can connect in series and parallel, that you have learned in work power energy. when two springs are in series, equivalent spring constant is, what is the equivalent spring constant when two springs are connected in series? K1, K2 divided by K1 plus K2. What is that in parallel? K1 plus K2. Series parallel combinations of springs are also asked. And comparison of time periods are asked. Comparison of frequencies also. Okay. Now, physical pendulum. Next illustration is physical pendulum. Physical pendulum is any rigid body which is capable of oscillating in a vertical plane about a fixed point over it. Then the rigid body may be of any irregular shape like this. You have somewhere fixed. Let that be the fixed point O, and an axis is passing through that point. Axis. Okay, the center of gravity of the rigid body is here. Say the center of gravity G. You draw a line between center of gravity and point of support. Let that distance be D. Okay, now you displace this rigid body totally through some angle. You rotate this rigid body totally through some angle. Rotate the rigid body totally through some angle like this. You rotate. Then what happens? Then this center of gravity also displaces slightly. It finds the new position G dash. Then what are the forces acting on it? When left from that position? One is the weight mg. Weight mg. Resolve that force into rectangular components. One along a line perpendicular to the radius. One along the radius. And this component, as this angle is theta, this component will be mg cos theta, and this one will be mg sin theta. About O you measure torque. Torque tau is equal to mg sin theta into d. Mg sin theta has only torque about O, because mg cos theta's line of action is passing through O. Any force whose line of action passes through the reference point, that force cannot exert any torque. But here mg sin theta, whose line of action is away from the point O, and that perpendicular separation is d, then mg sin theta into d is the net torque, and balance torque is equal to I alpha. So I alpha equal to mgd. You neglect theta here. Theta only for small angles this can execute simple harmonic oscillations. That is alpha equal to mg by I into d. Okay, alpha you got alpha. Now alpha can be written as omega square theta. So omega is root of mgd by I. Then time period is 2 pi root of I divided by mgd. This is the formula for time period of a physical pendulum. Okay, writing that formula once again, 2 pi root of I divided by mgd. If it is a simple pendulum has got a heavy sphere, heavy ball, but whose size is negligibly small, suspended by means of a light inextensible string from a rigid support, frictionless support. Okay, there moment of inertia I is equal to mass of that object sphere. Only massive part is that object sphere into perpendicular distance square, where L is the distance from point of suspension and center of gravity. That distance is d. Here simple pendulum, d replaced by L, m into L square, and d is equal to L. So time period is 2 pi root of ml square divided by mgl. 1l cancels, m cancels, you get 2 pi root L by g. 2 pi root L by g. Time period is 2 pi root L by g. 2 pi root I by mgd can be applied for any rigid bodies which is fixed about one point and oscillated about that point. Simple pendulum is one such. 2 pi root L by g. Time period of simple pendulum depends on length as well as acceleration due to gravity. T proportional to root L. When length increases, period increases. When g value is changed from one place to other place, you take the pendulum from one place to other place. Then also there is variation in period. Suppose you take a pendulum, simple pendulum from surface of earth onto some height. There the acceleration due to gravity is less. Then periodic time is greater. Let us develop a formula for that. T dash divided by T over an altitude h above surface. Then T proportional to 1 by root g. So T dash by T is as g divided by g dash. That is T dash by T as root of g by g dash can be written as g r square by r plus h whole square. So g gets cancelled. So T dash by T as, we can neglect that square within roots. So r plus h by r. So T dash is equal to T into r plus h divided by r. So T dash is equal to T into 1 plus h by r. That is T dash minus T as. T dash minus T as T h by r. That is T dash minus T by T as h by r. T dash minus T by T can be measured as the percentage change in the time period of a pendulum when taken to height h above surface of earth. Okay, if h is equal to r by 2, suppose you are taking the pendulum from surface to a height half the radius of earth, h is r by 2, then you get r by 2 by r, T dash minus T by T as 1 by 2, that is 50%. So value of g decreased, due to which periodic time increased by 50%. Oscillations has gone slow. When period increases means it takes more time to oscillate once and period becomes more. That is one of the applications. Suppose in some other cases, there may be a metallic pendulum which is not compensated, uncompensated metallic pendulum. On summer days, the effective length of that pendulum would increase, due to which periodic time also would increase. So how it affects? There, time period proportional to square root of L. There, T dash by T as root of L dash by L. There, the change in length due to thermal expansion, delta L as L alpha delta T, we have learned in chapter thermal properties. So that delta L is L dash minus L, which is L alpha delta T. So L dash is equal to L into 1 plus alpha delta T. That is T dash by T as root of 1 plus alpha delta T. 1 plus alpha delta T. Okay, so T dash by T can be root of 1 plus alpha delta T. Like this you can work it out. Okay. So in many other cases, suppose Earth has a cylindrical hole. Last year 2023 recent mains paper also the question was asked. Earth is given a cylindrical hole, frictionless hole. Across any of this chord, need not be its diametrical chord, whatever chord, it should be straight one, should be frictionless one. A small ball is left at one end. It can execute simple harmonic oscillations with the period T as 2 pi into R by G. That can also be written as 2 pi into R divided by G can be written as Gm by R square. Gm by R square, that is 2 pi root R cube by Gm. This on calculating you get close to 1.4 hours. Close to 1 hour 20 minutes. 84.6 minutes. Only it would take to complete one oscillation. Okay, this is the same as we have learned earlier in chapter gravitation, time period of a close orbit satellite. Also, we have learned a person on equator feels weightlessness when Earth turns once around. In this periodic time, that is 1.4 hours. Same answer for all these different types of questions. 2 pi root R by G is well-known relationship. 2 pi root R cube by Gm, all this you can by heart. Now, simple pendulum as well as spring mass system. The simplest applications of the simple harmonic motion that we have completed. Now we move on to damped oscillations. Damped oscillations are those oscillations where damping force is experienced by the body. Normally we discuss undamped oscillations. Undamped oscillations can go on continuously. Maybe a perpetual motion, but due to friction, all types of oscillations are damped. To maintain that damping, to compensate with that damping effect, we have to supply energy periodically to every oscillating systems. Damped oscillations are those oscillations having decreasing energy, decreasing amplitude, decreasing intensity. But damped oscillations can be simple harmonic provided the angular displacement is very small. Damped oscillations can be simple harmonic provided angular displacement is very small. Damped simple harmonic motion is only in our syllabus. Damped oscillations. For damped oscillations, what is reducing continuously? Energy as well as amplitude. There is a force which is a dissipative force, damping force, F damping, which is proportional to the velocity. There is a proportionality constant called coefficient of damping. Unit of damping coefficient is also important. Unit of damping coefficient is what? Newton divided by meter per second. That is Newton second per meter. Newton means kilogram meter per second square. Meter cancels, second cancels. So dimension of damping coefficient is kilogram per second. It's a very popular dimension. That is mt raised to minus 1. mt kilogram per second. mt minus 1 is damping coefficient. mt minus 2 is mt minus 2 force constant, surface tension. Last class we have discussed. Now mt minus 3 intensity. mt minus 1 damping coefficient. mt minus 2 surface tension or force constant. mt minus 3 intensity. So damping coefficient is F divided by V. Its unit is kilogram per second. By heart it. Damping force is minus BV. Then damping force depends on velocity. Velocity dependent force. Due to this damping effect, the angular frequency has been reduced. So periodic time is increased. But for simple harmonic oscillations, omega and period are constants, but amplitude is decreasing continuously. Let us see how amplitude is decreasing. For that, let us write the equation for the total force. Total force, net force is equal to minus kx minus bv. So the differential equation should be md square x by dt square plus kx plus b dx by dt equal to 0. It's a quadratic equation. When you solve it, you may get a solution like this: A dash cos omega dash t plus or minus pi. Here, what is omega dash? Omega dash is the angular frequency, constant angular frequency of the damped SHM. Omega dash is equal to root of k by m only for undamped oscillations, but minus b by 2m whole square, where b is that coefficient of damping, m is the mass of oscillating body. A dash is equal to a e raised to minus bt by 2m. So amplitude decreases exponentially. You go for a graph showing the variation of amplitude A dash on y-axis, t time on x-axis. At t equal to 0, its amplitude is maximum A, and it takes infinite time for that amplitude to decay to 0. That means it never meets with x-axis. That means it will take infinite time to meet x-axis. That means it doesn't have an x-intercept, but it has a y-intercept. Y-intercept is the initial amplitude. Okay, there is a famous solved exercise in NCERT textbook. Let me tell that more. After what time interval amplitude becomes half? That is, A dash is equal to A by 2. Put A dash equal to A by 2. That you get 1 by 2 equal to e raised to minus bt by 2m. So 2 equal to e raised to bt by 2m. Okay, then take logarithm on both sides, natural logarithm. Log 2 equal to bt by 2m. Log e is 1. That's why. Okay, let me write full steps. Some of you may not follow. So taking logarithm on both sides. Log e raised to bt by 2m. So log 2 equal to, this can be multiplied here as the coefficient, bt by 2m into log e. This log e value is 1. That I wrote before. That is, log 2 is equal to what? Bt divided by 2m. So what is t? T equal to 2m by b into log 2. That 2m by b into the value of log 2. Natural logarithm of 2 can be 0.693. So t equal to 2m by b into 0.693. You should know this much only. What is the mass of the oscillating body? What is the damping coefficient? Then you will get the time after which amplitude is exactly half the initial amplitude during damped oscillations. Damped oscillations are also treated as simple harmonic. In damped oscillations, amplitude decreases exponentially, but frequency is a constant, but it is a reduced constant while comparing with the undamped oscillations. Okay. Now, forced oscillations, that is the last topic. Forced oscillations and resonance. Forced oscillations and resonance. What are forced oscillations? We have learned that every oscillating bodies have their own natural frequencies. Every oscillating bodies may have one or more natural frequencies. Okay, some systems may have large number of natural frequencies. Some system have may have only one natural frequency. Some system may have few, 1 or 2 or 3 natural frequencies, like this. In mechanics or electromagnetism, these forced oscillations are so relevant. Then you can make any oscillating body oscillate with desired frequency. That frequency can be the frequency of the applied external periodic force. So any oscillating body can be made to be oscillated with the frequency of the applied external periodic force. So periodic force should be either a cosine or sine function. That's all. Okay. Then that frequency omega driver frequency, that may be less than the natural frequency. Omega 0 is representing the natural frequency. Omega d may be greater than natural frequency. omega d can be equal to natural frequency. So three cases arise there. Okay, then in the first case, the vibrating system will have smaller amplitude and smaller energy. Second case, when driving frequency greater than natural frequency, also the vibrating system has lesser energy, lesser amplitude, but when omega d equal to omega 0, the vibrating system has maximum amplitude, maximum energy. This phenomenon is called resonance. So resonance is the very important topic that to be covered here. Forced oscillations and resonance. Resonance is a special case where natural frequency of the vibrating system is equal to the frequency of the applied external periodic force. Then the system vibrates with maximum amplitude, maximum energy, system resonates. System resonates vigorously, vibrates vigorously. System has maximum energy then. Okay. That is called forced oscillations and resonance. There is a popular equation for studying this. That equation is used for finding out the amplitude of forced oscillations. So amplitude of forced oscillations given by f0 divided by m square into omega d square. Omega d square minus omega 0 square all square plus omega d square b square all to the power 1 by 2, where f0 is the force amplitude, maximum of the applied external periodic force, omega 0 natural frequency, omega d driven or driving angular frequency, that is omega d is the angular frequency of the periodic force. Maybe that periodic force Fd may be F0 cos omega dt, may be of this form. Then there is no confusion. B is the damping coefficient. Okay, now you plot a graph between the amplitude and the driving angular frequency. Amplitude on vertical axis. Amplitude on vertical axis and driving angular frequency on horizontal axis. Omega d on horizontal axis, amplitude vertical axis. You may get a graph showing this variation. Based on that equation, you try to draw this graph, you get like this. There, the amplitude attains maximum value when omega d value is equal to omega 0. When omega d is less than omega 0, when omega d greater than omega 0, all these cases amplitudes less. So the system resonates and the resonant amplitude may be written as AR. Then AR is equal to, what is AR? When AR, omega d equal to omega 0, so the first term becomes 0. So second term only appears. So f0 divided by omega d square b square raised to 1 by 2. As that square cancels here, f0 by omega db. f0 divided by omega db. This is the formula for resonant amplitude and is assumed to be the maximum value of amplitude for that vibrating system. Okay. Even that is constrained, that value is limited because of this coefficient here. Resonant amplitude proportional to 1 by b. As damping coefficient is greater in any case, then resonant amplitude is lesser. Damping coefficient depends on the nature of the surrounding medium of the oscillating body. Also, nature of the oscillating body, nature of surface finishing of oscillating body, only external conditions. Resonant amplitude is more when f0 is more. Resonant amplitude is less when omega d is more, provided f0 and b are constant. But AR proportional to 1 by b is very important thing. So any vibrating system can vibrate with maximum amplitude when the driving frequency is equal to the natural frequency of the vibrating body. That is called resonance. Many applications. Soldiers are asked to break their steps on bridges. Soldiers are asked to break their steps on bridges because bridges are naturally oscillating bodies. They will have some natural frequencies. Unfortunately, if soldiers are taking the march past periodically with the frequency as that of the natural frequency of the bridge may vibrate vigorously and it may even collapse. At least it may get damaged. Many applications are there. While you tune your FM channel 91.9 like that, you are tuning a resonance circuit, electromagnetic circuit. When that frequency manually you adjust in your mobile phone and that frequency slightly less than that characteristic one, some noise is heard. When the tuned frequency is greater than that characteristic frequency, also the same noise, but exactly at that frequency resonates. Then maximum energy transfers from the station to your device. So resonance is the phenomenon of maximum energy transfer. Very simple application. You take the case of any curry without salt, no taste. So you plot the taste on y-axis and amount of salt added to the curry on x-axis. So remember, salt on x-axis, taste on y-axis. As you increase the amount of salt gradually and gradually the taste increases. Taste seems to increase. Yes, taste is best at some value of the salt. But further addition of salt reduces the taste. Everything is like that in nature. It obeys this law of resonance. That is forced oscillations and resonance. But here, if omega d equal to omega 0, naturally it vibrates with resonant amplitude. But at that time, if damping coefficient is also 0, then the amplitude would become infinity. That never happens in a real life situation because damping is unavoidable. Damping may be reduced. All electrical measuring instruments are given certain sort of damping called critical damping. Critical damping. All measuring instruments, weighing balances are given critical damping. Suppose you are standing on a weighing scale. That weighing scale may be an analog type, old type, a needle type. You are getting onto it. Soon getting onto that needle comes to a stop at the corresponding reading. Suppose you weigh 50 kilogram, the needle exactly stops at 50 kilogram. It doesn't overshoot a bit because it is given a critical damping there in that instrument. Okay. A car, while the shock absorber of a car, it is given certain amount of damping so that it should not oscillate at all. The person sitting inside, when the car jumps, the person should not feel that it has jumped into a gutter. So this damping is a very useful one in daily life. Damping is needed. Damping cannot be avoided completely. Some extra damping causes loss of energy in the form of heat. But one more chance is there to be asked. That is, if omega d not equal to omega 0 system does not resonate. But if b equal to 0, then what happens? If b is 0, but omega d not equal to omega 0, then also you can find out an amplitude which is m into omega d square minus omega 0 square. And this is that amplitude at not at resonance, but damping coefficient is equal to 0. Okay, and that's all about forced oscillations and resonance. Don't forget to go through these many topics. Let me tell you once again. Simple harmonic motion, simplest of all harmonic motions. Any motion, any type of oscillation, any type of to and fro motion of reduced amplitude whose Acceleration is directly proportional to the displacement from mean position, a proportional minus x. That is the condition for simple harmonic motion. Y is equal to A sin omega t plus B cos omega t. Like this also you can express periodic motions. Okay. But the resultant amplitude would be root of A square plus B square. That is the resultant amplitude. This motion is also periodic. This motion is also periodic and simple harmonic. The periodic time is equal to 2 pi divided by coefficient of time. Coefficient of time is omega. So time period is 2 pi by omega. Amplitude is root of A square plus B square. Periodic time is 2 pi by omega. So the phase angle is tan phi is equal to phase angle made by the resultant simple harmonic motion with horizontal. Tan phi is equal to B by A. It can be also expressed as root of A square plus B square into sin omega t plus phi, where tan phi is equal to B by A. In that way, tan phi equal to B by A, you can find out the value of phi, substitute here. Okay, then you can get the equation for that simple harmonic motion. That simple harmonic motion has different amplitude. One more example. If you write y is equal to sin omega t plus cos omega t, then coefficient of sin and cos is 1. So the resultant amplitude is root of 1 square plus 1 square, that is equal to root 2. So tan phi equal to B by A, 1 by 1 is equal to 1. So phi is equal to pi by 4. So our equation can be written as y is equal to root 2 A sin omega t plus pi by 4. If this sign separating these two terms is negative, that will reflect here omega t minus pi by 4. So linear combination of two simple harmonic motions are also simple harmonic. Okay. Then the position of simple harmonic motion, A sin omega t, A cos omega t, all that very important. X is equal to A cos omega t. You go for x t graph, it should be a cosine curve like this. If you go for velocity, minus A omega sin omega t. What is the nature of velocity time graph? It is an inverted sine curve like this. Based on that situation given, you can try to plot that graph, that's all. But acceleration position graph is carefully drawn. A equal to minus omega square x. That should be a straight line passing through origin whose slope will be given A by x. A by x is equal to modulus of the slope is omega square. Okay, like that, if you go for graphs between position x and velocity v, that is elliptical. That was asked last year mains. If you go for acceleration and velocity graph, that also will be elliptical. Okay, now moving on to energy of simple harmonic motion, last topic. Energy of simple harmonic motion. Kinetic energy K is equal to half m v square. V square is equal to A square omega square sin square omega t for our reference. We started with x cos, so velocity becomes sine function. Potential energy is half m omega square A square cos square omega t. So total energy T is half m omega square A square, which is a constant. So kinetic energy is also periodic, but kinetic energy is not simple harmonic, because kinetic energy can be written as half m omega square A square into sin square theta can be written as 1 minus cos 2 theta by 2. See, that's why this cannot be simple harmonic, because it has two terms, 1 by 2 minus cos 2 omega t by 2. That format cannot be simple harmonic. So kinetic energy is not simple harmonic but periodic. What is the period? T is equal to 2 pi divided by coefficient of time. coefficient of time is 2 omega. That is T is pi by omega. Pi by omega. That means half of 2 pi by omega. Period is halved in comparing with SHM. Position, velocity, acceleration, force, all this execute simple harmonic oscillations. But kinetic energy executes only harmonic oscillation, means periodic oscillation, not simple harmonic motion. With a different period. What is the period of kinetic energy? Half. So what is the frequency of kinetic energy? 2 times. So frequency of SHM is half. Frequency of its kinetic energy is 2F. Frequency of its potential energy again 2F. Total energy is a constant, so total energy does not have any frequency. Okay. Careful. Sum of kinetic energy and potential energy is not time varying, is a constant. Kinetic energy is time varying, periodic, but not simple harmonic. Potential energy also like that. Total energy is a constant. So sum total of kinetic energy and potential energy is a constant and not harmonic also. But difference of kinetic and potential energy is harmonic and periodic with a period pi by omega. You can show it, you can subtract these two and you can come to know that we have discussed is true. Okay, with that I conclude the discussion, revision of the chapter Oscillations. We'll be meeting soon with the next chapter. Thank you.